Okay, so hello everyone. Welcome to LICD lecture 41D. And in today's lecture, we'll cover broadly two topics. Firstly, we will cover the first order active band pass filter. We'll analyze the circuit and we'll build up its frequency response and we'll cross check the value of the gain and the cutoff frequency and the passband gain in LT spice. Then secondly, we will do the design of first order active bandpass filter and we will discuss the various design steps and verify the design values in LT spice. Okay, so with this, let us start with the actual topic. Let me put it in the full screen mode. Okay, yeah. So let us start with lecture number 41D and let us start with the bandpass filter. Fine. Okay, so in case of a band pass filter, we have two elements in the feedback network, that is R2 and C2. Collectively, the impedance will be Z2, and the other element will be R1 and C1 in series, wherein the input is connected to the inverting terminal via these two components, that is R1 and C1, and their collective impedance is Z1. So the transfer function of this system will be PO of S upon VI of S. So it's a general structure of a non-inverting configuration. So whose formula is given by minus Z2 upon Z1. Okay. Now, since it is a linear application, that's why this is applicable. Now, Z2 will be R2 parallel to 1 upon S C2 and Z1 will be R1 parallel to 1 upon SC1. Okay, so we will clarify this. We'll solve this. R2 parallel to 1 upon S2 will be R2 into 1 upon SC2 divided by R2 plus 1 upon SC2, the whole divided by R1 plus 1 upon SC1. So if you simplify this further, you will get it in the form, if you simplify this algebraically, you will get finally this h of s is equal to minus s times c1 r1 divided by 1 plus s r2 c2 plus 1 plus c1 r1. Okay, so all these things will come with practice. So I will recommend that you write all these things on a piece of paper and verify the formula. Now, that being said, let us divide and multiply the entire numerator and denominator by R1. Fine. So we can isolate these terms together. So h of s can be written in terms of three terms now. So the first term is minus R2 upon R1. The second term will be S C1 R1 divided by 1 plus S C1 R1 into the third term will be 1 divided by 1 plus S C2 R2. So this is my equation of H of S. Okay. So equation number 1 has 1 0 at origin and it has two poles and its passband gain was given by minus R2 upon R1 if we consider the mod of it. So HOBP is the passband gain for the band pass filter, which will be given by R2 upon R1. And the remaining terms will be as it is. So your new expression of H of S will be HOBP. The second term will be SC1 R1 divided by 1 plus SC1 R1. And the third term will be 1 divided by 1 plus S R2 C2. Okay. Now, if you want to jump into the frequency domain for the frequency response, we'll have to convert S equal to j omega. So we substitute H of j omega is equal to HOBP. The second term will be j omega C1 R1 divided by 1 plus j omega C1 R1. And the third term will be 1 divided by 1 plus j omega R2 C2. Okay. So if we rewrite this in a more standard form, it will be H of j omega will be equal to HOBP. The second term will be j omega upon omega L divided by 1 plus j omega upon omega L. And the third term will be 1 plus 1 divided by 1 plus j omega upon omega L. So this is the generalized expression for the transfer function in frequency domain, where omega L is given by 1 upon R1 C1 and omega H is called as is given by 1 upon R2 C2. So from here, FL will be given by 1 upon 2 pi R1 C1. FH will be given by 1 upon 2 pi R2 C2. Now, this filter is useful with omega L very much less compared to omega H, in which case the omega L and omega H are called as the lower and the higher 3 dB frequency. Okay. So this circuit is used in the audio applications where it is desired to amplify within an audio range while blocking out the DC as well as noise above the audio range. So the frequency response will look something like this. So you have two frequencies, FL and FH. So only frequencies between FL and FH will be passed. That means it will be in the passband region. And if any frequency is below FL or above FH, it will be rejected and they are in the stop band region. So the maximum gain you can achieve over here is HOBP. And if you come root 2 times lower than HOBP, you will get that exact 3 dB frequency. Okay, so this is the frequency response of a band pass filter. Now let's simulate this with the circuit component values and check it out. R1 we take it as 100K, C1 as 80 nanofarad, R2 as 100K, and C2 as 80 picofarad. So the passband gain will be given by R2 upon R1. In this case, it will be 0 dB. So HOBP will be 1 unity, but in dB it will be 20 log to the base 10 of 1, which will be 0 dB. And the lower minus 3 dB frequency FL will be given by 1 upon 2 pi R1 into C1, which will be equal to 20 Hertz. And the higher 3 dB frequency will be given by FH is equal to 1 upon 2 pi R2 C2, which will be 20 kilohertz. So as you know that 20 Hertz and 20 kilohertz covers the entire audio range. So basically we are trying to design a filter which will pass all the frequencies between 20 Hertz to 20 kilohertz. Now let's check that in simulation. Let me reduce this and open up the, yeah, so it's already, the circuit is already made available. Here the components are already taken as R2 is 100, R1 is 100, C1 is 80 nano, and C2 is 80 pico. Okay, so let's simulate this and check out what are the results are. So it should pass audio range basically. So I'll run this and yeah, we are getting a similar response. So whatever we have discussed in the theory, exactly similar thing we are getting over here. As you can see very clearly, the circuit to your left hand side is what we have discussed, and the circuit to your right hand side is what is a simulated frequency response in LT Spice. Now let's check the 3 dB frequency. So this is the, first of all, let's check the passband gain. So the passband gain is clearly 0 dB as we have predicted. And let's check the upper and the lower cutoff frequency. It should be 20 Hertz and 20 kilohertz. So let's check that out. So we go 3 dB down from here. So 3 dB down will be somewhere around here. Okay. So this is around minus, almost like a minus 3 dB. It is around 19.98, which is 20 Hertz. That's good. And here we will check now the second one. Okay. Second one is also this is also 3 dB down. It's also 3 dB down. Yeah. Okay. I have to adjust it properly. 3 dB. Okay, so we are getting two frequencies. And the FL will be instead of 20, it is 19.98 hertz, and FH will be instead of 20, we are getting 19.45 kilohertz. That's the audio range. So that's how this filter works. So between this 20 hertz and 20 kilohertz or 19.45 kilohertz, all the frequencies will be passed. And below 20 hertz and above 20 kilohertz, all the frequencies will be rejected. So this region from 20 hertz to 20 kilohertz is my pass band, as you can see, pass band. And after that, we have a stop band wherein the gain reduces at the rate of 20 dB per decade. And here also beyond FH, that is 20 kilohertz around, the gain also reduces at the rate of 20 dB per decade. Okay, so that's the frequency response for a band pass filter. And we have verified these numbers. Now let's proceed further. So these were the simulations which were carried out, and these were the results which we have seen that. Now comes the design. Let me go back to the full screen mode. Okay, so we have to design a bandpass filter with a gain of 20 dB over the audio range. Okay, so again we have to for FL and FH equal to 20 hertz and 20 kilohertz with a gain of 20 dB. Okay, so we know the audio range is 20 hertz to 20 kilohertz, so very easy to write FL is equal to 20 hertz and FH is equal to 20 kilohertz. So for a gain of 20 dB, HOBP of 20 dB will be 20 log to the base 10 of 10. So if you substitute 20 log to the base 10 of 10, you will get R2 upon R1 as 10 because HOBP is R2 upon R1. So we can select the value of R1 as 10K, so R2 will be correspondingly 100K. Okay. Now we'll come back to the cutoff frequency. Your FL is given by 1 upon 2 pi R1 C1, which is 20 hertz. So from here, FL we know, R1 we know, we can calculate C1, which is coming out to be 0.7858 microfarad. So we select the value of C1 as 1 microfarad and we rescale the value of R1 and C2. Okay. So basically we take the standard value of C1 and we recalculate the value of R1 and R2 accordingly. So if you rescale, the R1 will become 7. Okay, actually it is 70. Okay, R1 is will be 100 times. R1 will be 10 times actually. There is a mistake. R1 will be 10 kilo ohms into your, please note this mistake, it is 10 kilo ohms into 0.7958. So it will be 7.87 kilo ohms and R2 will be 78.7 kilo ohms. Okay. And though that's why if you select C1 as 1 microfarad, R1 will be 7.87 kilo ohms, R2 will be 78.7 kilo ohms. Now, if you calculate, now only C2 is left. So FH will be given by 1 upon 2 pi R2 equal to 20 kilohertz. So if you put everything in the form in the calculator, the values you will get C2 as close to 100 picofarad. Okay, so this is your design circuit where R2 is 78.7 kilo ohms, C2 is 100 picofarad, R1 is 7.87 kilo ohms, and C1 is 1 microfarad. Now let's check whether it's giving you the proper results or not. Okay, so let's open the LT Spice. And first of all, open the design. So I've already created the design just to save time. Okay, so this is my design circuit. Okay, so this is my design circuit for a passband gain of around 20 dB and cutoff frequency FL was 20 hertz and FH was 20 kilohertz. We have taken the similar values as we have discussed over here. Let's see that again. Okay, so R2 is 78.7 kilo ohms, C2 is 100 pico, C1 is 1 microfarad, and R1 is 7.87 kilo. So we have taken exactly those values. Now let's simulate this. We click on run and we check the output. Yeah, the nature of the graph is correct. Now let's confirm some numbers. The passband gain was supposed to be 20. Let's check how much it is. It's around 19.99, which is close to 20. So that is verified. So the passband gain we got achieved 20 dB by this design. Remember, we want a passband gain of, as given in the design, gain of 20. Okay, and now we have to check the FL and FH value. If FL and FH is 20 kilohertz or no, or 20 hertz or no. Okay, so let's go 3 dB down. That is around 17 dB, close to 17 dB. Okay, this is around close to 17 dB. As you can see, the frequency is 20.36 hertz. Let's check at a higher frequency now. Okay, so this is also close to 17. Okay, this value was uh, close to 17. Okay, let's check this number also. I think it is not exactly 17. Okay, so around 17 dB, close to 17 dB, we are getting around 16.59 kilohertz. So that's okay. Audio range we defined it to be 20 hertz, 20 kilohertz, and we are getting around 16.59 kilohertz. So actually, there is a slight deviation in the higher cutoff frequency. That is due to the first order nature of the filter. So over here, the I think if I tweak it properly, let me check it out. Oh, no, around 17 dB. It's around 16 point something. So we are not getting 20 kilohertz. We are getting 16.23 kilohertz. So that's the problem if a system has, it has one zero and two poles. So you have to select all of them very, very carefully. Then only you get this result. Okay. So we are getting a FL and FH as 20 hertz and 16 point something, 16.5 kilohertz. So that's quite deviating from the higher cutoff frequency. But it's fine. We are getting audio range, and the graph is behaving as a band pass system. Only thing is the higher cutoff frequency is a little how we designed the band pass filter, first order band pass filter design. So I think that's it for today's topic. Next time we'll start with second order, KRC filters. So until then, have a good day and thank you.